So describing unusual features for our graph, there's a few things we want to be careful of. We want to look for if there are multiple modes or not. Often this shows that there are subpopulations or some characteristic that's actually separating values. And this can also be shown by gaps in the data. So like this example down here, there's two modes, there's kind of these two peaks, there's also this big gap. So what they're measuring here are the weights of different pennies. So they collected some pennies and then they weighed them. And what this shows is that there's these two subgroupings of weights. And looking this up, these pennies here are actually our current pennies. And pennies nowadays are actually lighter because they use zinc. Whereas these are the old pennies, I think it's pre-1982 pennies. And these used copper. So what this shows is that within our data set, there are these subpopulations or something actually separating it. So that's an unusual feature we want to be careful of. Another unusual feature we want to be careful of are outliers. So outliers are kind of extreme or unusual values, and that they're not fitting with the trend of everything else. So where we have most of our data over here, what we can see is there's this one value out there. Let's see, average monthly expenditure, that just means someone spent almost $7,000 in a month. But that's not usual. Most people are spending much, much less than that. So it's this unusual case, and when we make our conclusions for our data, we just want to make note of those cases. We're going to end up doing later is actually having a way to calculate whether or not something is an outlier, because then maybe we could make the argument, maybe that's an outlier, and we just further calculation. So that's how we would describe unusual features. Now what we want to get into is how do we describe the center and spread for our data? We make our histogram and graph it. How do we describe the middle and how it spreads away from the middle? So center's the middle position or value. We're going to talk about the difference between kind of those two wordings there. It's the average or the typical value. Another wording that's used is expected value. If we know where our data is centered, we get an idea of where we expect to land. So like looking at this graph up above, we expect to land in this range here. We also want to know is the spread of the data. How close to this expected view? Is it really close by or really spread out? Because then all of that will tell us about trends within our data. We're going to branch into two different ways of describing center and spread. If we have skewed distributions, we want to use median and this thing called interquartile range. Why we want to use these values is because they're based on location within the data. And why that's good is that it avoids influence from these outliers that can come through. Median and interquartile range, they don't really take into account that value there. They know there's some value out there, but they're not using that number of 7,000 in any sort of calculation. So median and interquartile range, they'll focus more on this middle of the data, which is exactly what we want to do. So this is great for skewed distributions like this. For symmetric distributions, which are nice and just kind of raise up to the middle and then decrease away, for this we want to use mean and standard deviation. And these are based on the actual value. So we're going to have two forms of center, two forms of spread, and in terms of our description and our conclusions, we just want to take note of what does the graph look like, because then that'll tell us which center and spread we should use. Because if it's skewed, what we'll see is the mean, since it's actually calculated based on value, it's going to take into account that 7,000, and where we should be in the middle here, it might pull that mean to the right a bit. So then that means influenced, and it's not as accurate of a center. So let's go into how we calculate these. Calculating median. We want to find the physical middle value. First thing you should always do is if you're doing this by hand, make sure the data is in order. from smallest to largest, which is already organized here, so we're all set to go. What we want to end up doing is if we have our block of data, we want to cut it in half, such that 50% of the data is over here, 50% of the data is over here. And this will be our median. So this comes through in two different ways. If we have an odd number of values, the trick that I use is I just take 2 fingers and move towards the middle, taking one value off from each side. So when we have an odd number of values, we're going to be placed at an actual number for our median. So for us, that middle value is 12. And if we imagine this kind of wall that 12 creates, with 12 being part of the wall, what we can see is there's an even number of data values above and below, and that's exactly what we want. So our median is 12. If we have an even number of values, if I do that same trick of take 2 fingers and kind of move towards the middle, I'm going to be stuck between 12 and 15. So this kind of wall that we're imagining is landing in between those 2 values. So for our median, we actually average those numbers. So you take 12 plus 15 in half. So our median is a 13.5. So this is where median's just based on location. Doesn't matter what numbers are out here in the ends, like this 20 could actually be 2,584. It doesn't matter because it just gets covered up the same as we move towards the middle. So that's where the median isn't influenced for outliers, so it's great for skewed distributions. For symmetric distributions, we want to use the mean. The mean's a more accurate calculation of center. So, some notation. For median, there's no special notation. We usually just write out the word median and equals number. For means, we have these different symbols, and we talked about these earlier. If it's a population mean, you use that symbol mu. If it's a sample mean, you want to use X bar. So it just depends on where's the data coming from. Is it a sample or a population? Most often we'll have sample data, so we'll stick with X bar for today, but in the future we'll see some population data, so we'll kind of switch between the two. So, the formula. What we can see is there's this big symbol here, this big Greek symbol, and that symbol there is sigma. And what sigma tells us to do in mathematics is it just tells us to add. It's a summation symbol and saying we're going to add things together. Whatever's next to it, that's telling us what we want to add together. So it's telling us to add together x values, and for us the x values, those are just our data values. So it's telling us to add up our data values numerator, which when we calculated the median above, that's what we did here. We added up our 2 values that we wanted to average, so that 12 and 15. Similar idea here, it's just we're adding up. In the denominator is some new notation that we definitely want to get used to using because it'll pop up all through the course. N is for sample size. Basically, how many values are we working with here? So let's look at calculating the mean for our 2 scenarios up above. So let's go to if we had an odd number of values, where we have 3, 8, 12, 15, and 18 in the numerator. And then divide by how many there are, which there are 5 values. And we just want to plug that into the calculator. And if you plug this into the calculator, just be sure to be careful with that numerator together before dividing. And this will give you a mean of 11.2. If we calculated the mean for our even number of values, same process. You add up that 3 and 8, 12, 15, 18, and now we have the 20 as well. And then divide by how many values there are, which there are 6 numbers now. So our average would be 12.67. So we get out these 2 averages and can kind of compare that there is a difference with the median. They should usually be close by. If the mean and median aren't close by, then that's telling us that there might be some outliers influencing things. So thinking about how do the mean and median work together with these different distributions. If we have a symmetric distribution, they should be pretty much the same. Our median would be landing right in the middle here, and so would our mean when we average the values out. So if your mean and median are close together, that suggests a symmetric distribution. When we're skewed left, a quick way to find the median is it's usually where the peak is. So if this is our graph, the median would be where the peak is. For our mean, if it was symmetric, if I just cover that up, if it was symmetric, our mean would land in the same spot. But we're throwing in these small values, and if we throw in all these small values to average with, the mean gets influenced, gets pulled to the left, which is part of the skewed left vocabulary. So our mean would be somewhere. So if you find these two values and the mean is significantly less than the median, that suggests that it's skewed left. Alternatively, skewed right, if our median's at the peak and we have these large values coming through, the mean's going to get pulled towards those larger values. So in skewed right, the mean's going to be larger than the median. So this is a tool that we can use that if from the graph itself we can't tell if it's skewed or symmetric, look at the numbers. Compare the numerical values of mean and median.